Hello. So in the previous few lectures, we looked at longitudinal modes of a cavity, which essentially constrain the frequencies at which light oscillates within constraints, which is that of a one-dimensional cavity, which is a set of two mirrors placed at an appropriate distance with an appropriate curvature to ensure stability of the field. And then what we are asking next is what is the transverse structure of the light which is confined in such a cavity. By transverse, I mean the direction of propagation of the light is along the axis of the cavity, and we are looking at what happens in the orthogonal directions, which is in a plane that is a field profile within a plane which is perpendicular to the axis. To get to this, we will first approximate our exact wave equation to something called a paraxial wave equation. And from there, we will look at solutions of that. There is a certain benefit to this because intrinsically the wave equation permits all kinds of fancy solutions. We are interested in solutions that are spatially more or less varying very little as they propagate along the direction set by the axis of the cavity. So because of that, we want to get to this paraxial approximation, which makes life a little bit more simpler. Right. So let me first write down the wave equation. And so our wave equation can be written down in this fashion, which is del square operator on the electric field, which is a function of space and time. And you have 1 over c square. This is for the propagation in free space, wherein the velocity of light in vacuum comes in. And this is the temporal second derivative of the electric field. And this is the wave equation. Now you see, I make the first approximation, which I'm looking at a scalar equation. A scalar equation implies that I drop the the polarization degree from the electric field. That is, my equation is that of del square E RT minus 1 over c square dou square E dou t square RT. These are indeed functions of the vector of position, but the electric field themselves is considered as a scalar quantity. Now, this simply is to simplify and do something reasonably analytically. So one of the important things that this does, the polarization doesn't really change of the field. So that is an important consequence that we should keep in mind. So one should not look for polarization effects when one is the governing equation is a scalar wave equation. The other important point to note that the validity of this equation will certainly, as we will see, will depend on the paraxial approximation. And this equation has been used to, for example, discuss to a large extent diffraction, interference, and all these kind of effects. Um, but do realize that this is not the exact solution governing the electromagnetic field, because what we require is a vector equation, which is the equation number one, right? And uh, to solve this becomes challenging, and polarization effects can then be very systematically be done by following through the solutions of this vector equation. Anyway, so let us focus on what we need. So what we are doing is looking for solutions of this equation, that is ERT, of the kind where the spatial and the temporal parts actually separate out. That is, the amplitude is a function of R, and we are looking at a monochromatic field which has got a very specific harmonic time dependence. So time dependence, if any, is of this kind. Now if I plug this solution, this I would let me call that as a ansatz. if I plug this solution back into this wave equation, the scalar wave equation, then what I get is basically the del square E of R plus, so you see that the dou by dou t square will bring out a minus I omega two times because the second derivative, and what you get is basically a omega square hanging around there, and the c square was already there, and this is equal to 0, and this is precisely what we call as the Helmholtz equation. So now we are going to look at, let me call this equation number 3, and this is the equation that is our governing equation for a light that is monochromatic. After all, why we are doing this is because we are interested in the spatial structure of the light and not so much about the temporal content, which we have anyway fixed by looking at the longitudinal modes of the cavity early. Right. Now, you see, you are very familiar with one of the solutions. This is one solution, right, of this wave equation, right, which is called the plane wave solution, right? So plane wave solution goes in this kind where my E of R becomes E naught, some constant amplitude, exponential I, K being my wave vector dot R, right? This is my plane wave. You understand the nature of this field. Let me quickly draw. For example, if I am propagating, if this is my K vector, which is the propagation vector, then I can draw a plane, right? So this is a plane, and you would see that in this plane, you will see that for, so for example, let me draw my coordinate system. So for, you can see that for any r position vector which ends up on this plane, so let's say there's a point on the plane and you're looking at any vector r, so you see that k dot r would be a constant on such a plane, and hence essentially this light is characterized by these sequence of planes which have got different values of the phase as r evolves, right, along the direction which is basically set by the k vector or the propagation vector of the field. So that is the kind of, uh, the structure that one has in mind. Now please note that this is a rather unphysical sort of a field, simply because there is an infinite transverse extent. This plane extends to infinity, right, in all directions, right? This is infinite plane. So this is clearly unphysical because such a wave would have infinite energy content. But this is a very uh, useful solution simply because it forms the basis for Fourier analysis. So in that sense, these are extremely useful. That is, if you give me any arbitrary field, a realistic field, I can always expand it as a sum of such plane waves with different values of k. Right? So in that sense, it's a very powerful tool for understanding, and hence it is used very widely. The second solution to that, to the equation number 3, is again of a similar kind which you are familiar with. This is what is called as the spherical wave, right? That is, I have got now E of R for the spherical wave is some E naught by R exponential I k times R. Here k is simply the magnitude of the wave vector k. Now again, you see, this is a very interesting solution. What we have is essentially, uh, you know, a constant amplitude, if you like, in spheres centered around the source, for example, and the amplitude itself falls like 1 over r, so that the energy falls like 1 over r square. uh, what it means is that the constant energy is flowing out from such a system. One can quickly check that this is indeed the solution of the wave equation. So if you look at the spherical, that is, you write down del square in the spherical polar coordinates, then you see that the radial part, I expect you to go home and verify this. The radial part of the del square operator will go like 1 over r square dou by dou r times r square dou by dou r operating, right, on E of r, right? So this is precisely what is the radial part of the del square, and you will see that this will turn out to be simply some constant, which by the way is just minus k square, times E of r. Please go home and check it, and indeed then this forms the wave equation, the solution of the scalar wave equation. So now what I will do is I'll come to the other approximation of the scalar wave equation, which is called the paraxial approximation. Right. Paraxial, what I mean is largely I have got a direction of propagation. Let me call that Z or equivalently R. And I'm interested in fields which are largely propagating along that direction, you know, uh, and uh, there is little variation in, for example, of the field along this propagating direction, right? And one is not interested in, as you know, for example, if you look at a laser beam output, the extent of the transverse extent of the beam can be as little as a few millimeters or centimeters, depending on how far you're observing. So we are interested in a region which is quite small, right, in this transverse direction in comparison to its propagation along z, right? So that is the kind of picture that one has in this notion of something which called paraxial. Paraxial implies parallel to the axis, paraxial approximation. So mathematically what it involves is that if I look at my the r vector, and then I'm looking at only its magnitude, right? In that, then I can clearly see that Cartesian coordinates I can write down as x square plus y square plus z square, and then take a square root of it. Now you will clearly see that I'm interested in z's which are much much larger than either x or y. No, that is precisely what is the paraxial uh, region. So what I do is I rewrite this as x square plus y square plus r square, realizing that my r is now much larger than x and y, where I can bring out my r as common, right? And this I can write it as 1 plus x square plus y square by r square. And this quantity's square root. Now I do know that my second term here, right? This term, this term is extremely small in comparison to 1, right? Because we are looking at such a narrow region about x and y. Uh, so essentially this square root can be expanded, and what I will do is basically retain only the first term in this expansion. That is, I can write down my k times r, right, which is simply multiplying that as approximately k times capital R plus k times x square plus y square by 2r. I had an expansion of 1 plus epsilon, epsilon being much smaller than 1 to the power of half, I'm approximating this as 1 plus epsilon by 2, and there are of course higher order terms, and I'm retaining only the first, right? So, and now you can of course, if I say that this is my approximation, so now if you look at the validity of this equation, you see that the next term in this expansion would be minus epsilon squared by 8 and so on. So the this approximation is valid if the phase, remember this is k dot r is the phase term. If the phase due to this third term is much smaller than 2 pi, you would see that clearly uh, one can approximate this whole series to just what I have written down here, right? So to ensure that, that would mean that in my result would be that k times, uh, let me call, I'm calling x square plus y square as some a square. So my k times a square by, this is going to be the next term, right? And this has to be much smaller than 2 pi. So if you expand your 2 pi by lambda, that is my k, and there's a factor of r, and I can write this as a square less than or equal to 2 pi times r square by a square, right? So that gives me the regime of validity. That is, if I have a square by r, right, is much smaller than r square by a square, then that is going to be my region of validity for such a approximation, right? This. So what we are doing is we are seeking a solution of a particular kind, and the solution is such that I'm looking at that my E of R, the spatial part of the electric field, is simply E naught of R, which is some amplitude, times a large spatial dependence on the Z, which is coming out of shear propagation, right? And this is not really a constant, but what we want it to be is we want it to be a slowly varying function of Z, the the axis or the major direction along which the propagation is the largest. Essentially, the slowly varying dependence on Z can be written down mathematically in this form. That is, my uh, variation of the electric field, the second derivative, for example, along Z, please note, is much smaller than 1 over lambda, the first derivative of E naught of R along Z, which by the way should be smaller than 1 over lambda square E naught R itself. So is that what one is stating is the following, that my the variation of the amplitude is slowly varying. Change of the amplitude with respect to Z is much smaller than the field itself, and its variation of the change is even smaller, right? So this approximation as is given a formal name, and this is what is called as slowly varying envelope approximation, or in other words, It's captured by this acronym SVEA, right? So let me just pictorially tell you. What one is saying is that I have got a wave. So let me just draw the. So what one is saying is that there is hardly any change in the amplitude along a lambda distance, right? This is along my propagation direction, and the variation, if any, is extremely slow. That is across over tens, hundreds, thousands of lambdas, right? I've just exaggerated the variation here, but I hope you get the point. What one is saying is that this amplitude variation is extremely slow in comparison to the propagation of scale, which is lambda itself. So given such an approximation, what is the consequence of this on the electromagnetic wave? And that is where we will come to the paraxial wave equation, right? So I'm writing down the following, I'm writing down my wave equation, which was my equation number 3 on the top, which was del square E of r, and we have made the approximation now that my E of r is such that it is E naught of r, which is the amplitude, times exponential I k times z. So let us use the slowly varying envelope approximation and use it back into the Helmholtz equation and see what we get. So the first, uh, the most important uh, claim that we are making is that we have chosen z to be the direction of propagation, right? That is a very important step here, where we have essentially lifted the symmetry of the problem, or rather defined a preferred direction along which we want to propagate, which is along z. And because we have chosen z as a propagation direction, this there is a factor exponential I k z as the phase that explicitly comes in, right? So let me go back and look at now our del square operator. So the del square operator is shown here, and here what you have is the derivative with respect to x, derivative with respect to y, which are the orthogonal direction or the transverse directions, and second derivative with respect to z. Um, so what I will do is I will retain this uh, the derivative with respect to x and y as it is, and I will call this part of the operator as delta t square. So this contains the transverse directions, and we retain it as it is because the slowly varying envelope approximation that we did has got to do with the propagation along z. So let me plug in this ansatz which I have chosen here, right? I plug in this ansatz into this equation and basically do the second derivative with respect to z. You can check this for yourself at home, and what we get is an expression of this kind. So we have the following derivatives which are there with respect to z. So remember that our E naught of r is actually a function of x, y, z, and we have made the slowly varying envelope approximation which has got to do with its dependence along the z direction. So these derivatives come in here. The second derivative with respect to z, there is a first derivative with respect to z, and obviously in comparison to these two terms, we have already said that the variation, the second derivative is much slower than the variation with respect to first derivative, and one can basically neglect this term, right? So this term is neglected in comparison to the first derivative. So I retain only this term and then rewrite my Helmholtz equation. So my Helmholtz equation takes this form. You have the second derivative with respect to the transverse variables. Then you have the next term, which is the first derivative with respect to z. And then you have the constant term or the field itself without any derivatives, and the omega square over c square term, which is coming from the Helmholtz equation. So this is equal to 0, and clearly we know that there is a space-time dependence between the wave. So the spatial periodicity and the temporal periodicity are related, and this is nothing but the relation between lambda and nu, with wherein c comes in, and factors of 2 pi make it this way. So you can quickly derive this relationship from the fact that c is simply c equals to nu lambda. You can use this to derive this relationship. So these two terms get cancelled, and what remains is the paraxial wave equation. So this equation clearly has two terms. Let's just understand them carefully. The first term is the second derivative with respect to the transverse degrees of freedom, which is x and y, and only the first derivative with respect to z and nothing else. So that is our paraxial wave equation, and it is this equation that will use to obtain the transverse modes of a cavity. Let me first give you the motivation of or the kind of modes that I want to obtain when I'm looking at the transverse profile of the field within the cavity. So you see, I have chosen my z direction clearly, and my z direction uh, is the direction along which the mirrors are placed, right? And the field along x and y is symmetric, yes, and it is peaked at the center, which is peaked along the axis uh, uh, of the cavity. Right, that is the kind of field that I want. But typically, because in a laser, when you look at the output, you see that there is a central maxima and the field dies out very neatly on either side in the transverse direction. So the kind of form that I have for the intensity as the output intensity will be of this kind, where my intensity is a function of x, y, and z, and there is a Gaussian distribution which is centered around x equal to 0, y equal to 0, right? And it has got a Gaussian distribution. So that's a distribution I've tried to capture in this plot here on the left. And it has the W basically gives me some sort of a width. So this is a Gaussian function which you recognize, right? And there is some amplitude factor here. So this is the intensity that I expect from a Gaussian beam. Of course, what we are solving for is not intensity, but the electric field itself. So I guess the nature of the electric field, right? That is what I want to figure out. So I have clearly made the paraxial approximation. So I have this form for the electric field, right? The exponential ikz term is simply coming because I have chosen that to be the long axis, and that is the direction in which the field evolves. So that is certainly the first time dependence at the scale of lambda, which is already captured. And then you have E naught of r, which should in principle give me this intensity which I get, right? So I make a sort of a assumption as to what should be the form for this E naught of r. Okay, so the assumption I make is the following. I have already chosen the intensity to be Gaussian, add an amplitude factor A, right? A Gaussian phase factor, and rather than fixing my width of the Gaussian beam, I have kept the width to be a function of z. See clearly here, q is a function of z. So that I think we have to be very clear about. So this q I have chosen to be a function of z. There might be an extra phase factor along p, so I have chosen that to be some p of z, because after all we are not any longer talking about a plane wave, so there might be other phase factors as the field evolves. And there are a few important caveats that q of z, which acts like the complex width here, I am allowing this q to be a complex number. What it would mean that the real part of q will obviously give me a sort of a width for this complex Gaussian phase, and the imaginary part of this will actually combine with this imaginary, so that eventually when I square it, mod square it, to get the intensity, I would basically get this Gaussian distribution. This Gaussian distribution is important for intensity, for which I require this term to be sort of real. Because if this was purely real, this whole term would be in the complex conjugate, this phase will be simply lost, right? So I want the Q to be complex. I'm allowing that uh, that Q to be such. So I'm writing down this very carefully, that the Q is my generalized width of the Gaussian beam, which in principle can be complex. So this is the kind of form I have chosen for my electric field. And what I do is I take this as my ansatz, right? And I plug this back into my paraxial wave equation, which I just described above. So remember, the paraxial wave equation has the derivative, first derivative with respect to z. So that is precisely what I have here. I've calculated it. Now clearly P is a function of z, right? And Q is a function of Z, right? So these are the explicit dependencies that come in, which I've highlighted here. And so if I do this, I would get the following form. Again, I expect you to write this out for yourself and carefully calculate each of these terms. Similarly, there is a derivative of the E naught of R with respect to the transverse variables, which is second derivative with respect to X and a second derivative with respect to Y. These again from the this exponential phase factor, right? From the exponential phase factor, one will get the x and y, the explicit dependencies on x and y. So you get this second term. So now I have put this back, these two terms back into my the so-called paraxial wave, right? So the paraxial wave equation contains these two, which I have collected term by term, and this should be equal to 0. Now that's the paraxial wave equation. Now to choose that to be equal to 0, I do the simplest thing at hand, which is to choose that my dq over dz is actually equal to 1, right? This is giving me this equation, right? And the dp over dz, I have chosen it to be I by q. So like just ensuring that these two conditions are satisfied, I will see that the whole coefficient for my E naught of R, independent of Z, or for that matter x and y, is always going to be equal to 0, because I've chosen these two terms to be solutions of this constraint. So these form the constraint that ensures that my paraxial wave equation is satisfied. So once I do this, I get a particular form. So from dq over dz, I get that q of z is some q naught, which is at z equal to 0 plus z. And from p of z, I get this logarithmic dependence that you can think of, right? That is my, because you see, after all, I have to, the q itself is a function of, is a linear function of z. So I would get this log here. So this is, and I have chosen my z equal to 0 to be a special position. So at z equal to 0, I have chosen that my q equals to q naught. And at z equal to 0, I have chosen that my log of 1, which is basically p at z equal to 0, is 0. This is my choice, um, without any loss of generality, right? So what has happened is the following, that I have got an explicit form for q, and I got a relationship between p and q as well. And if you recall, we wanted a certain, um, we wanted that our Q, the generalized width of the Gaussian beam, to be a complex quantity, right? So utilizing that fact, what I expect is I construct a form which is complex for the generalized, for the width. So there is a real part to it, right? And there is an imaginary part to it. And you can clearly see, if I plug in this imaginary part back into that, I will quickly so look at it here. If I plug this q of z into this exponential, the uh, the complex, the complex Gaussian phase factor. So I will quickly, get this, and I will get two terms. The real part will give me this just the complex phase, whereas the imaginary part will actually give me precisely the Gaussian intensity. When I square it, there will be a factor of 2. That will precisely be the Gaussian intensity that we get, right? So uh, I am basically, ensuring that this is how the field will look like. Um, then I have the other phase factor, right, which is captured by the P of Z. So my P of Z, if I put it, I know the form for P of Z, exponential I P of Z with the logarithm sitting there will actually look of this kind, right? So in my exponential I P of Z, I get this factor of Z over Q naught. So Q naught is the Q at Z equal to 0. So if I plug this Z equal to 0, I'll basically get a R naught and a W naught square, right? This W naught and R naught are precisely the values of R and W taken at Z equal to 0. So what I do is I basically ensure that at Z equal to 0, my face front is the radius of curvature, right? This is essentially giving me the radius of curvature. If my radius of curvature is infinity, then I would get basically a planar face front, right? So what I'm doing is at Z equal to 0, that special location, I am demanding that my face front is that my radius of curvature of the face front is infinite. That would mean it's a planar face front. So that is at Z equal to 0, R is infinity, and hence 1 over Q naught is simply this complex number. Only the imaginary part of it is what is remaining. Now let's see what is uh, R and W as a function of Z. We know that at Z equal to 0, I have R of 0 is infinity, correct? And at Z equal to 0, W of 0 is simply W naught, right? That is my width of my Gaussian beam. Now what about its Z dependence? So I can simply write it out. So remember that my Q goes like Q naught plus Z. So I expand it, you know, and then uh, I will essentially get the Z dependence here. This is my, let's just call that as left hand side. On the right hand side, I have actually, so I already come up with the complex form for this. And what I do is now essentially look at, identify after equating the left and right, I identify what is R of Z. That is what is the radius of curvature of this phase, right? Uh, and what is the width as a function of Z. So if I identify that, these are the two terms which I get, right? That is my R of Z, sort of uh, increases for very large values of Z, essentially it just linearly increases, right? And W of Z, which is the width, has this particular form, has this form. So again, let us be very clear. I have introduced a new term called Z naught, which I call it the Rayleigh range. Z naught is simply the relationship between the width, which I mentioned here. In a sense, what happens is we have scaled the variation of the curvature as well as width in terms of Z naught, which seems uh, like a very natural scale for Z. So essentially, what I get uh, is the following form for the radius of curvature of the phase as well as the width as a function of Z. Now we can clearly put it up here. So for example, at Z equal to 0, you see that I'll get R to be infinity, right, which is consistent with what I have chosen. And at Z equal to 0, the W should go to W naught. So you see the minimum width happens at Z equal to 0, where it's W naught. And at Z equal to Z naught, the W naught basically increases to W naught times square root 2. So that kind of gives you a measure of the way the width is increasing as you vary Z. right? So z equal to 0 is a special location. Z can take negative as well as positive values, and clearly you see that the radius of curvature changes sign with as you change z, right? Right. So this is the first term, that is the spherical phase, with a width, with a generalized width and so on. Now the second term is this exponential IP of z, right? And this term also we are looking at it carefully. So so this term of course is such. What I'm doing now is clearly there is a complex number sitting at the bottom. So I'm removing the magnitude and the phase factor separately, and you can see that this is what I get. I can write down this complex number, right, as a magnitude part, which is 1 by 1 plus square root of 1 plus z square by z naught square, and a phase part, which is exponential minus I phi of z, where phi of z is simply the ratio between z and z naught. So eventually what we have is the full electromagnetic field which satisfies the paraxial wave equation, where coefficient is just E naught of r. E naught of r has got this form. This a was already there. There is a square root of 1 plus z square by z naught square that is coming from that exponential IPZ. So you see that the magnitude is sitting here. So what happens is as z increases uh, away from z equal to 0, the amplitude sort of decreases, right, as 1 over z. Clearly you want the amplitude to decrease as 1 over r or 1 over z, captured by this the factor p. And then you have the Gaussian phase factor, the purely Gaussian phase factor, where r is a real quantity, and you know that r is actually at r z equal to 0, this is infinity, so you get a plane wave here. But for any other finite z, you get a curved wave front. And you have this was the real part of the q, which was generalized width. This is the imaginary part that gives you this the amplitude, which has got a Gaussian width, right? So exponential minus x square plus y square divided by w square of z, where w is a function of z. So now let me look at it pictorially, what this implies and why this is a beam-like solution. So this is my z-axis, and clearly z equal to 0 is a special position. In green I have drawn W. So W, this is the locus of the points of equal intensity, if you like. So clearly W is increasing, right? Is minimum at z equal to 0 and is increasing on either side. Z equal to Z naught is a location where W naught goes from W naught to W naught times square root 2, right? So that is the kind of distance Z naught. This distance is what I mentioned above, is called the Rayleigh range. And clearly as Z is negative, the the radius of curvature becomes negative. So you can see that I'm drawing in blue basically the wavefronts. And similarly, when Z is positive, the radius of curvature is positive, and you have this the radius of curvature other way around. And you have the intensity, which is largely centered about the axis, and it exponentially dies out on either side away from the axis. So W naught is called the beam waist. So for the Gaussian beam, clearly there are three parameters, independent parameters, which is W naught, right, which is the beam waist, right? Once I fix W naught, I have fixed even Z naught, right, which is my Rayleigh range. If I choose my amplitude and wavelength, which I have to choose for any beam, right? So there's only one single parameter that completely describes the Gaussian beam, right, which is simply the beam waist. And that is what is so interesting about this very nice solution that essentially captures the lowest order excitation, of the kind which peaks at the center very naturally into a in a appropriate cavity, right? So now one can ask, what is the angle at which it diffracts, right? What is the angle at which the beam is expanding, if you like? So one can write down that as angle as small angle approximation with simply the W divided by Z, that as you decrease W naught, right? That is, as you make the beam narrower at Z equal to 0, the beam base is narrow, the the angular divergence of the beam is going to dramatically increase, right? That is the form for the Gaussian beam. And of course, please remember that this E naught of R, for the complete solution, the E naught of R needs to be multiplied by, so I will write that out. The E naught of R needs to be multiplied by uh, exponential I k z, and it also needs to be multiplied, if I'm not looking at the Helmholtz part, looking at the frequency of the field, this has to be multiplied by exponential minus I omega t. So right, so these two factors one has to keep in mind, which is of course there. This is just the amplitude part that gives us a Gaussian beam solution. So the Gaussian beam solution is not the complete story which we have obtained. One can in general look for solutions which are sort of higher order excitations of the field. I want to mention this only for the sake of completeness, uh, in the sense that just I had a ansatz in which the field was basically cylindrically symmetric, but that need not always be the case. One can look for solutions in which in the Cartesian coordinate, for example, where the field along x and the field along y need not be symmetric, right? So fields of this kind are certainly possible. So again, I'm looking at the Gaussian beam solution. So I do have the similar, phase factors with the Q being complex. I have the usual exponential I p of z. This needs to be multiplied by exponential I k z that is separate, that is coming from my paraxial approximation. And all that I have done, that in my prefactor, I have put in now two functions, okay, g and h, which are functions of x and y independently. So they could have, there's of course a scale to it. It's a function of x by w and y by w. W gives you a width of the beam in the transverse direction, right? So there is a scaling there. And it so happens if you plug it back into the Helmholtz equation, you get g and h to be Hermite polynomials. Right? So they have explicit form. One can actually solve it. And and you see what one is doing is you are constraining the field along the orthogonal directions, right, which is along x and y, as well as in the z we had put in the mirrors. So you see again you get this only some form of this functions are allowed. This is the Hermite polynomials which have a integer index n and m, right? So my field no longer is uh, you are no longer free to take any value, and the lowest value of n equal to 0, m equal to 0 is indeed 1, which is what we got earlier as our Gaussian beam solutions. So as you increase this n and m, right, you get higher order excitations of the same Gaussian beam, because the Gaussian field is the same, but all that you have is now factors of Hermite polynomials, multiplying it as a prefactor, right? The important thing to note, I have drawn, for example, the field distribution, or the electric field distribution associated with the n equal to, which is along the x, n equal to 1, right? And along y, m equal to 0, right? This is this excitation. The index will tell me the number of minima, right, number of nodes that the field will have apart from the nodes at infinity, right? So along the x direction we have one node, but along y there are zero nodes, right? So that is the kind of form that you get. It has got a consequence with respect to the phase or the frequency which is supported. Now uh, think about it. When we had a plane wave, we said that the frequencies which are allowed within the cavity were simply integer times c by 2l, right? These were the frequencies which are allowed. L can take integer values, and c by 2l was the appropriate frequency. So once you have this transverse structure, one can ask, is this the final mode which is possible? Do these conditions get modified? That's the question that one is asking. And indeed, these functions get these frequencies get modified, this condition. And the way to do that is you should look at, for example, the phase accumulated. Look at the whole phase, right? The phase is coming from the exponential ikz as well as the exponential I phi 1 and phi z, which was there, right? Minus phi z. So look at the total phase at z2, which is kz2, minus the the phase at z1. So what you have is kz2 minus phi at z2 minus kz1 minus phi at z1, right? So that essentially is the difference in the phase that you have. Now imagine that for a field that it is a allowed mode of the cavity. What does that demand is that if I go around a round trip and come back to myself, that is I come back to Z itself, right? If I come back to the same location Z, I should have covered in this round trip n times integer times essentially, right? 2 pi. Only then this is going to be a mode, right? It's going to coherently add up. If it was any other value for multiple round trips, that field will actually get cancelled out. So it has to be a multiple of 2 pi. Now clearly if my round trip is giving me 2 pi, a single traversal from mirror number 1 to mirror number 2, that is the location of the mirror uh, Z1 to Z2, should give me a phase factor of pi. So you can put this all together and you can figure it out for yourself that you will essentially get the new frequencies, new longitudinal frequencies to be new LMN. Remember that L was coming from the longitudinal boundary condition. M and N are coming from the transverse boundary conditions. It's C by 2L, the usual one, L plus 1 by pi m plus n plus 1 cosine inverse G1 G2. So this precisely happens for the higher order Gaussian mode. I would like you to determine for yourself this condition for the lowest order Gaussian mode, which we have already discussed, right? So this is my second comment which I want to make about the Gaussian beams. The third comment which I want to talk about is the validity of the paraxial approximation. Now you see this approximation is going to be valid. Remember we had derived this condition very early on. So indeed that needs to be valid. If this condition is not satisfied, then the form of exponential minus x square plus y square, limiting it to just that, will be incorrect, right? And not just that, we want to make sure that the the size of a mirrors are such that they reasonably, reflect the whole Gaussian field across. So imagine if my size of the mirror was small, like this red thing which I have made. So there will be diffraction effects at the edges, and then of course the Gaussian beam solution will no longer be valid. So let's be very clear about that. Uh, Now, when I wrote down this above condition, I'm writing down in terms of G1 and G2. Remember G1 and G2 were the parameters we got for stability of the cavity, which is simply 1 minus L by R1 and 1 minus L by R2, right? Now, uh, recall that both G1 and G2 have to have the same sign, right, for the cavity to be stable. If you have opposite signs, then this cosine square root is going to be a problem. And indeed, Gaussian beams are not solutions of unstable cavities. These are solutions only of stable cavities. So that's an important caveat, that our Gaussian beam solutions, even the higher order solutions, are solutions of a stable cavity. And hence there is a convention of doing this. So when I give you, for example, a problem to solve and to calculate the stability of two given mirrors, if the mirrors are concave, we use positive values for the radius of curvature r, and if the mirrors are convex, negative values for the curvature r, right? And of course the stability criteria is exactly the same as we have discussed earlier. So these are some comments that essentially finishes our discussion on the spatial transverse and longitudinal profile of the fields within a cavity. So the next thing which I'm going to talk about is basically start off with the model of the active media. So to begin with, I will go through the classical description of the active media, then add a little bit of quantum details to it, okay, and then we will go to the complete description. But then, just like I dealt with uh, the field, I want to deal independently with the media and then put the medium inside the cavity and look at the laser. All right. Thank you.